My presentation is the parametric study of the crack growth behavior of high-density polyethylene under the combination of mechanical and oxidative degradations. The content of my presentation is here. First, I explain the introduction of my research and background of the stress corrosion cracking of the thermoplastic, and the explanation about the numerical modeling for stress corrosion crack growth, and the parametric study for the validation of the suggested model, and the final conclusions will be covered. This picture illustrates the hoop stress dependency of the failure mechanism in the thermoplastic pipe. At the higher load level, the ductile failure occurs with the localized buckling, resulting in hydrobursting or the ballooning. And in the intermediate load range, the brittle fracture occurs with the slow crack growth, such as fatigue crack growth or the quick crack growth. And at the lower load range, the contact time with the aggressive environment are increased, and the chemically driven brittle cracking occurs. Such environmental mechanism is called stress corrosion cracking. In many cases, the field failure mechanisms of the thermoplastic pipe is considered as either brittle or environmental fracture. This picture shows the stress corrosion crack in the inner surface of the polybutylene pipe. Thermoplastic pipes are usually exposed to not only the mechanical loading such as internal pressure or bending loading or axial loading, but also the chemically aggressive environment. And chemical degradation of polymer is generally induced by the oxidation. The oxidation-induced stress corrosion cracking frequently causes a dramatic reduction of the lifetime of the thermoplastic pipe due to the reduction of molecular weight and ductility, and it causes the toughness decrease and embrittlement. This picture shows also the failed polybutylene pipe due to the stress corrosion cracking. This multiple micro cracks is a typical characteristic of the stress corrosion cracking in the thermoplastic pipe. There are four stages of the stress corrosion cracking. First, the initiation stage of the multiple micro cracks, and slow growth of the individual cracks, and next there are interaction of the cracks and the formation of clusters, and finally cluster growth grows to the instability, and it leads to the ultimate failure. In my research, we concentrated on the slow crack growth of the individual crack under the aggressive environment. One of the famous thermoplastic high-density polyethylene is frequently used for water or natural gas pipe, liquid gas distribution pipes, and HDP shows a simple wedge shape of the damaged zone in front of the crack tip, and with the clear boundary with the undamaged material. And in case of high-density polyethylene, there are several slow crack growth modes, such as discontinuous or continuous mode, depending on the load level and temperature. And such a complex slow crack growth kinetics can be simulated by using the crack layer theory. So the research objectives are the development of generalized simulation method for individual stress corrosion crack growth with chemical degradation by using crack layer theory, and parametric study for the important parameters to validate the suggested model. Okay, next let me explain about the crack layer theory simply. Crack layer is a system of main crack and the surrounding damage zone, which is called the process zone. And the thermodynamic force, the TF, or the process zone growth can be explained by using the Gibbs potential energy variation with the process zone length. And the thermodynamic force for crack growth also can be explained similarly. The J, PZ, and JC are the energy release rate at the crack tip and at process zone tip and the crack tip respectively. And R sub T means the volume of amount material to be transformed into the process zone. And the 2 gamma means the specific fracture energy of the transformed material at the crack tip. And at the discontinuous crack growth, during the crack arresting time, 2 gamma is decreased with time. And gamma transform means the energy required for cold drawing per unit volume. And by using the linear relationship, we can calculate the process jump growth rate or the crack growth rate by this simple explanation. And as I mentioned before, the 2 gamma specific fracture energy at the crack tip is degraded with elapsed time. In the stress corrosion cracking, this is degraded due to the mechanical and the chemical loading. The mechanical degradation equation is adopted from the previous research. Here the 2 gamma is decreased function in time, specific fracture energy, and 2 gamma 0 means the surface fracture energy, specific fracture energy of the fresh material, and T sub I means the elapsed time from beginning of material transformation to process zone, and T star is the characteristic time of the mechanical degradation. So the T star must be a function of mechanical loading conditions such as fatigue R ratio or fatigue frequency. Next is a decrease in the specific fracture energy due to the oxidation. The oxygen concentration at the crack tip is utilized as the oxidative degradation index in this study. And it can be modeled by one-dimensional oxygen diffusion into the semi-infinite medium from the crack tip. And first, we use the carbon equation of Fick's law, and the C is the oxygen concentration along the process zone, and D is the diffusion constant of the oxygen in the process zone. And we can use the simple initial condition and boundary condition. And here the K is the oxygen influx coefficient, and it must be a function of electrochemical environment and loading condition. So it is a very important function in this model. And C sub max means the saturation concentration of oxygen. And by using the Laplace transform, we can obtain the analytical solution of the oxygen concentration along the process zone, like this. And by taking the x equals 0, we can obtain the solution of oxygen concentration at the crack tip. And by using the superposition method, the mechanical and chemical decay of surface fracture energy can be explained like this. And eta function is introduced to consider the oxidation rate depending on the polymer structure or antioxidant in the polymer. And we must consider the oxidation induction time in case of we simulate the oxidation of plastic. And generally before the OIT, the diffused oxygen reacts with the antioxidants mainly. However, in case of the polypropylene or branched polyethylene and polypropylene, the hydrogen atoms attached to tertiary carbon or the branched point are susceptible to abstraction by the free radical. So it accelerates the oxidation process. So we must consider in this case we must consider the slight degradation before the OIT by the chemical degradation. And after the OIT, the diffused oxygen reacts with the polymer chain, and there are dramatic reduction of the surface fracture energy before the OIT. And our simulation condition is here, the compact tension specimen under the constant load contacting with the abrasive chemicals in room temperature. The specimen geometry is given here, and the simulation algorithm is also given here. We can consider the OIT for the SDC thermoplastics in this region. Okay, this is the result of the parametric study. This figure shows the effect of chemical degradation. As you can see, the lifetime of the stress corrosion crack is not shorter than that of the creep crack growth only. And under the mechanochemical degradation, the surface fracture energy decays faster due to the combination of crit and chemical degradation. Thus, the average stepwise crack arresting has a shorter duration. In this figure, the solid line is the crack length, and the dotted lines are the crack layer length. Next is the influence of oxygen influx coefficient, K. The increase in K means the faster oxygen diffusion, and it induces also the larger amount of the oxidation. So it promotes the decay of the surface spectral energy, and so finally the lifetime is decreased with the K. Next is the average crack growth rate versus the stress intensity factor at the crack tip. As you can see, the initial region, the average crack growth rate are quite different with the K. So it means that in this region, the chemical degradation serves as a dominant effect on the surface spectral energy degradation. But if you take a look at this region, the average crack growth rate are gathering regardless of K. So it means the mechanical degradation serves a dominant effect in this region. So we can divide into the two zones. And the lifetime is reduced as the influx coefficient K. So this model shows the appropriate tendency about K. Next is the influence of the degradation rate before the OIT. If there is no weak point on the polymer chain, there is the oxidation rate before OIT can be negligible. So it can be modeled the low value of phi, normalized value phi, and if the polybutylene or polypropylene, we must consider the slight degradation before the OIT, and it must modeled by the larger value of phi. So the increase in phi, the faster degradation before the OIT, so the crack jumps faster, and the total lifetime also decreases. The final parametric study is about the oxidation induction time. The increasing oxidation induction time makes the beginning of the direct degradation later, and the critical YT. Sorry.